Hello everyone, and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about Faraday's Law and Lenz's Law, some of my favorite topics in E&M, because it really starts to tie the entire course together. Our objectives include recognizing situations in which changing flux through a loop will cause an induced EMF or current in the loop, calculating the magnitude and direction of the induced EMF and current in a loop of wire or a conducting bar when the magnitude of a related quantity such as magnetic field or area of the loop is specified as a nonlinear function of time, so changing magnetic fields or areas, and analyzing the forces that act on induced currents to determine the mechanical consequences of those forces. So let's talk about what Faraday's Law tells us. Faraday's Law talks about the induced EMF, the induced potential due to a changing magnetic field. It says it's equal in magnitude to the rate of change of the magnetic flux through a surface bounded by a circuit. So moving charges create magnetic fields. Changing magnetic fields move charges by creating potential. Now, the direction of the induced current is given by Lenz's law. So you usually use Faraday's law and Lenz's law together. So here's Faraday's law. The induced EMF, typically written with the script E, is the opposite of the time rate of change of the magnetic flux through that surface, of the magnetic flux. Or if you expanded that out, it's the opposite of the derivative of the integral over the open surface of B dot dA. And the EMF is the integral over the closed loop of E dot dL. That's your EMF, your potential around the closed loop. And if you don't have any changing magnetic flux, that actually becomes Kirchhoff's law. Kirchhoff's voltage law. So, Lenz's law is this negative sign right there. That's where the Lenz's law piece comes in. So we have our surface, we have magnetic field through it, and the area is changing, or the magnetic field strength is changing, leads to an induced potential difference in the circuit. The direction of that, whether it's going clockwise or counterclockwise, that piece comes from Lenz's law. So let's go to Lenz's law here. The current induced by a changing magnetic flux creates a magnetic field opposing the change in flux. Or the way I like to think about it is if something's changing, Lenz's law, the induced current or the induced potential difference, wants to counteract that. As an example, if we have this magnet being moved down into this loop of wire so that the magnetic flux into this loop of wire is increasing, the induced potential, the induced current, wants to oppose that. So if it's increasing down into that loop, it wants to create a magnetic field that opposes that up out of the loop. And as I do that with my right-hand rule, if the magnetic flux, the magnetic field strength, is coming out of the loop is what it's trying to oppose, wrap the fingers of your right hand around that, and you will see that you will start to get a current in this direction, that counterclockwise direction. You can also look at it from the perspective, let's draw another one over here. We've got a north, we'll put a south right beside it. We'll draw our loop of wire. If this time we have our magnetic flux, there we go, coming through there, but now we are moving our magnet away from that loop of wire, well, Lenz's law says that it wants it to stay the same. It doesn't want it to reduce. So it's going to create a current in the wire that's going to want to maintain that. So it's going to increase the magnetic field strength down through the wire. By the right-hand rule, that means our current must be flowing that way if we are moving our magnet up out of that loop. So that's how Lenz's law works. And it's really just a matter of practice. So here we go. If we have a sample like this, if the magnetic field is increasing, we're going to induce a clockwise current. Why? As we take our thumb and point it out of the page, if it's increasing, we want to oppose that. So to oppose that, we go the opposite direction, wrap the fingers of your right hand, and you get clockwise. If that magnetic field strength there is decreasing, Lenz's law says you want to work to maintain where it was. It doesn't want to decrease. That means you need to add magnetic field coming out of that loop. So point your finger coming out, thumb coming out of that loop, wrap the fingers of your right hand around that, and you're going to get the counterclockwise current. So more examples for Lenz's law and how you apply it.